Hi, so I will give you a little bit explanation for this lab 3 amplitude modulation and frequency modulation sinusoid signals. So if we add several sinusoid each with a different frequency fk, then our formula will be look like this, where amplitude k ak multiply by exponential uh, j phi k is the complex amplitude of the kth complex exponential term. So the choice of fk will determine the nature of the signal. Then we'll talk about the frequency modulated signal. So in if the frequency varies as a function of time, where the constant frequency sinusoid is the argument of the cosine, then we can say the angle of this signal is the exponent of 2 pi f naught plus phi. And you have to notice that this angle function changes linearly versus time, so it should be linear. And if you do derivative of this term, you will get the 2 pi f naught, which equals the constant frequency of the cosine in radian per second. You have to note that this is the radian per second, not in degree. So so in generalize, if the equation is like this, a cos phi t equal to real of this exponential term, then then derivative of this angle, you will get the instantaneous angular frequency omega I equal to derivative of psi t, and that is in radian per second. But we prefer hertz, so you have to divide 2 pi to get the frequency in hertz. And I noticed that some of the students don't know what is the difference between W or angular frequency and the frequency. So this is the angular frequency, and this one is the frequency. So you have to notify that. So then the chip, what is the chip signal? So chip is a sinusoid whose frequency changes linearly from a starting value to an ending one. And for the chip signal, then psi t is defined by this equation. So if you take the derivative of this equation, you will get the instantaneous frequency fi equal to 2 mu naught 2 mu t plus f naught, where the slope of fit is equal to 2 mu naught. So uh, if if we plot this frequency versus time, then you so if you plot the chip signal, you will get a signal like this. So if our first frequency is this one, and if the ending frequency is f2, then your slope will be 2 mu, and this signal, this frequency changes would be linear like this. 2 mu is the slope of this equation, and where the intercept is equal to f naught. If the signal starts at time t second, then f naught is also the starting frequency. Okay, we'll now I'm copying the code from 2.4 section, and if you run this code, you will get a so I'm using spectrogram here, instead of using the plot, because if you use the plot, you cannot infer the signal. But the spectrogram will tell you how the frequency is changing during the whole time. So how instantaneous frequency is changing starting from 0 to 2.1.8 second. So here we can see is starting from 100 hertz and ending at near to the 2000 hertz, and this is linear. That's why this is called chirp signal. So you have to use the spectrogram. You have to put your X here, and this is called window size. That will define what is your pixel. I mean, how much would be big window length. And the third element, you have to put your sampling rate. You can seek help from MATLAB about a spectrogram. You can try like spectrum. If you seek help, then it will tell you that a spectrogram is a short-term Fourier transform. Spectrogram has been replaced by spectrogram, so you can also seek help for the not spectrogram. But we will use a spectrum here because it's easy to use. So if you seek for the spectrogram and go to the documentation, it will tell you like a spectrogram. If you put one input, then window. So if you use one element in the function spectrogram, then it returns a short Fourier function STFT of the input signal X. And if you use X and window, then window to divide the signal into segment and performing windowing. But if you use the three parameter like X window and non-overlap, then non-overlap is the samples of overlap between adjoining segments.